Hello, class. The last section we'll discuss is thin lens. Thin lenses are those whose thickness is small compared to the radius of curvature. They may be either converging, which is figure A, or diverging, which is figure B. Parallel rays are brought to focus by converging lenses. Knowing that the dashed lines represent the normal for each surface, from Snell's law, we can see that each ray is bent towards the axis when the ray enters the lens, and then again when it leaves the lens at the back of the surface. For a thin lens, the focus length is the same on both sides. A diverging lens, which is thicker at the edge than the center, makes parallel lines like diverge. The focal point is at the point where the diverging rays would converge if it were projected back. Now, optometrists use the reciprocal of the focal length to specify the strength of eyeglasses or contact lenses. This is called power of the lens, where P is power. And the power of the lens is positive if it is converging, and negative if it's diverging. Here's ray tracing for thin lenses. Ray 1 is drawn parallel to the axis, therefore it is refracted by the lens so that it passes along a line through the focal point behind the lens. Ray 2 is drawn to pass through the other focal point, F', and emerges from the lens parallel to the axis. Ray 3 is directed towards the very center of the lens. This ray therefore emerges from the lens at the same angle as it entered. The point where these three rays cross is the image point for the object point. Because the rays actually pass through the image for this case, it is a real image. Now for diverging lenses, we can use the same three rays, but the image is upright and virtual. Note that ray 1 is drawn parallel to the axis, but does not pass through the focal point F' behind the lens. Instead, it seems to come from a focal point F in front of the lens. Ray 2 is directed towards F' and is refracted parallel to the lens axis by the lens. And then ray 3 passes directly through the center of the lens. Also note that the eye does not distinguish between real and virtual images. Both are visible. The thin lens equation is the same as the mirror equation. Note that the focal length is positive for converging lenses and negative for diverging. The object distance is positive when the object is on the same side as the light entering the lens, otherwise it's negative. And then the image distance is positive if the image is on the opposite side from the light entering the lens, otherwise it's negative. And this, you know, that the height of the image is positive if the image is upright, and negative, then otherwise negative. Now, diverging lenses always produces an upright virtual image for any real object, no matter where the object is. And then converging lenses can produce real inverted images or virtual upright images, depending on the object's position. The magnification formula is also the same as that for a mirror. For upright images, magnification is positive, and for inverted images, the magnification is negative. Alright, so for our first example, what is the position and the size of the image of a 7.6 centimeter high leaf placed at 1 meter from a 50 millimeter focal length camera lens? The first step is that we'll start with the lens equation. Rearrange it to solve for the image distance. Note that I'll keep the units in centimeters, so the focal length is 5 centimeters and the object distance is 100 centimeters. Plug and chug to get 0.19. Take the reciprocal to get the image distance to be positive 5.26 centimeters or 52.6 millimeters. Now for the image height, we'll use this equation. We know the image distance is 5.26 centimeters and the object distance is 100 centimeters. The object height is 7.6 centimeters. Plug and chug to get the image height of negative 0.4 centimeters. The negative means that the image is inverted. For our next example, an object is placed 10 centimeters from a 15 centimeter focal length converging lens. Determine the image position and size analytically and using a ray diagram. Alright, so analytically, it's the same exact steps that we've done before. So plug and chug, and we get an image distance of negative 30 centimeters. The negative means that it's to the left of the lens, or in front, and therefore it is virtual. Now the magnification is 3 times larger than the object, and it is upright because it's positive. Now here's the location of the image through using a ray diagram. So we just saw that converging lenses show either real inverted images or virtual upright images, depending on whether the object is in front or behind the focal point F.